We're joined today by Dr. Julian Newman in what is the second video in our series showcasing the work of the Nonlinear and Biomedical Physics group at Lancaster University. Now, Systemic Creative has been supporting the group to commercialise some groundbreaking medical technology developed based on the theories developed by the group and patents which they now hold. And this group is doing some fantastic, interesting and really impactful work. So check out the link in the description below to their webpage where you can learn more about their activities. And a quick word before we get stuck in about our sponsor, Easy Skips Online. Now, a skip company is an odd choice to sponsor a science video, we get that, but it turns out the guys at Easy Skips are just super cool and love a bit of science. So if you need a skip or you're interested in the company, there's a bit more about them at the end of the video, and of course there's a link in the description, so check them out. Let's go and meet Julian. Julian has worked at Imperial College London, the University of Bielefeld in Germany, Lancaster University and at the University of Exeter. And he's one of the most entertaining speakers on mathematical topics that I've had the pleasure to listen to. So I'm sure you're going to enjoy this talk. Julian is going to take us through time frequency analysis and the multi-scale oscillatory dynamics analysis toolbox, or MODA, which was developed here at Lancaster University. There is a link where you can download MODA in the description below from GitHub. You'll need MATLAB to run it, although there is a Python version in development. Over to Julian.
Hello, I'm going to be giving a brief introduction to MODA. So, traditional time series analysis methods are based on the following mathematical framework. You imagine that your recorded signal, that I've denoted lowercase x of t, which is a sort of finite time signal, as any recorded signal. So it's assumed to be a finite time segment of a sample realization of a stationary stochastic process, which I've denoted uppercase x of t. A stochastic process is a sort of probabilistic process, has randomness in it, and then stationary means that the law, or the sort of probabilistic description of this process, doesn't change over time. In other words, it doesn't make any reference to any kind of reference time or external clock. Stationary stochastic process can range from something as simple as a sine wave with a random initial phase, random relative to the time of recording, or it can be something as complicated as white noise. But the key point is that its statistics or its probabilistic description doesn't change in time, and the assumption is that your recorded signal comes from such a stationary stochastic process, and then the goal of the time series analysis is to estimate parameters of the law of your underlying stochastic process using the sample data that is your recorded signal. Now, this framework is not appropriate often for studying signals that come from systems that are influenced by their ever-changing environment. The stationarity assumption isn't appropriate, and therefore nor is the probabilistic assumption. Often that's inappropriate too, because that itself often is implicitly contingent on the stationarity assumption. MODA, which stands for Multiscale Oscillatory Dynamics Analysis, is a toolbox of time series analysis methods developed in the Nonlinear and Biomedical Physics group here at Lancaster University, specifically for these kinds of systems. So in particular, it's focused on identifying and quantifying the time-evolving characteristics of oscillatory components within time series data, and looking at time-evolving interactions between oscillatory components in time series data. So when I say oscillatory components, these are sort of, well, oscillations in your signal that are likely to come from oscillatory processes that exist within the system system that you're recording from, or that influence the system that you're recording from. And Moda has tools for studying univariate and bivariate time series data. So univariate means just a single recording, and bivariate means two simultaneous recordings recorded from perhaps different parts of your system that you're recording from. And so this kind of approach can particularly help to understand time-dependent phenomena, such as frequency modulation, so when a process has its frequency gradually changing in time, or intermittent synchronization, so oscillatory processes are sometimes synchronized and then sometimes not synchronized. And these time-dependent phenomena are often masked by non-time resolved methodologies, i.e. the methodologies that are rooted in the framework of stationary stochastic processes, where the parameters that you're seeking to estimate don't change over time. And in particular, the approaches of the time series analysis methods in Moda can often help avoid the mischaracterization of important, relatively simple deterministic mechanisms as noise, or chaos, or higher complexity than it really is. And all those three, noise, chaos, and higher complexity, can sort of mathematically be represented as approximately different forms of each other. So let me say a bit more about the sort of conceptual motivation behind why these kinds of approaches are important. So if I have a digital signal, lowercase x, recorded from a physical system, we'll call it S. Often we want to understand the oscillatory processes within S, or that influence S, that can be picked up by the measurement of your signal X. And so a fairly common basic procedure for identifying these oscillatory processes is as follows. I apply the fast Fourier transform to my signal. I then plot a graph of the Fourier amplitude, or the Fourier energy, which is just the modular square of the Fourier transform, against frequency. And then if I have in this graph a clear peak at some frequency f0, then that may suggest an oscillatory component of frequency f0 in my signal. Or if I have a clear peak at some frequency f0 plus some smaller peaks at integer multiples of f0, then that might suggest a non-sinusoidal oscillatory component of frequency f0. So these integer multiples of my fundamental frequency f0 are called harmonics. And then lastly, if you have a component in your graph that has a downward linear trend or a horizontal linear trend when viewed from a log-log axes, then that may indicate noise in your signal. So that is a fairly common sort of basic procedure, and I now want to look at an example. So this is going to be a graph of basically the Fourier energy normalized in a certain way. Exactly what I described on the last slide is for a typical procedure. But this is going to be applied to a simulated signal, X. It's going to have 200 data points per second, and the duration of the signal is over 20 hours, as you can see. And so what you can see is loads and loads of these small, really sharp, identifiable peaks. And I should say, these peaks, that's not due to the discretization of the frequency axis. The frequency axis is extremely finely discretized. And so what you have are values of 0 associated to almost all of the frequencies, but then in between these 0 values are a number of sharp peaks. I think I counted 93. And so the question is, well, what does the signal X look like that is likely to have generated a graph that looks like this? Is it 93 separate sinusoidal oscillations, or is it some large number of non-sinusoidal oscillations? So there are sort of a combination of fundamental frequencies and harmonics. Well, let me now show you what happens if I do the same thing for the same signal, but with just the last 50 seconds chopped off. So I have a new signal Y that is going to be my original signal X minus the last 50 seconds. So it's still 200 data points per second, but the duration is now 50 seconds less than it was before. And now we see a fairly significantly different looking graph. So let me just flick back and forth between the two. So here is X, my original. Here's Y, where I moved the last 50 seconds. X again, Y again. This raises the question, so is there something special going on in the last 50 seconds that means that just that last 50 seconds suddenly makes this huge difference to how the graph looks? As we see, it's really not very obvious what exactly is going on in the signal, and someone, at least who's applying the methods in a relatively naive manner, might assume that there are loads and loads of sinusoidal or non-sinusoidal oscillatory contributions or components in the signal, and that something really drastic has happened in the last 50 seconds. Those who are perhaps more experienced in these methods might think, well, maybe something else is going on, but in any case it would be hard to really say exactly what's going on in these signals, and you could easily be misled into mischaracterizing what the signal X is. Well, let me now show you, through a different representation, what the signal X really looks like. This is a wavelet power spectrum for just the first 12.5 minutes. So what is this wavelet power spectrum? Well, again, it's a representation of the oscillatory components. But what you see here, so on the horizontal axis is time, on the vertical axis is frequency, so these are both independent variables, and then the dependent variable is graphed by color coding. So this is effectively a three-dimensional plot where the third dimension, the dimension for the dependent variable, is the color coding. And so for each time, if you look at the vertical strip, then the graph of color coding against frequency is your representation of the frequency content of the signal locally around that time. And so what you see is that this signal X is actually just a simple linear superposition of two simple, fairly slowly frequency modulated oscillations. And there are no harmonics here, so these are sort of time locally approximately sinusoidal. So I have two frequency modulated sinusoids, and I've just added them together, and that's generated my signal X. Right, so if you look at this graph of the wavelet power spectrum, you see lower frequency oscillation and this up and down wavy motion. That corresponds to the fact that the frequency itself is being gradually increased and decreased. And then similarly for the higher frequency component, you see this wavy motion for the frequency modulation. That is how the signal looks for the entire duration. So nothing special was going on in the last 50 seconds. And the details of this are in the Moda manual. And so the conclusion is that time-resolved analyses are needed for signals that come from systems that interact with their changing environment, right? Because what I've got here is this frequency modulation, this time-evolving characteristic, and that is what has given rise to this sort of rather bizarre-looking result for the Fourier transform that treats the entire signal in one go, as if it sort of has no time-evolving properties. So let me say more about the foundational method in Moda, and that's time frequency analysis. So this wavelet power spectrum that I showed you earlier, that is an example of a time frequency analysis. So time frequency analysis gives a description of the oscillatory content of a signal locally around each time. For example, the ear performs a time frequency analysis on the air pressure time series that it receives, and that's how we hear. So here's an example of a time frequency analysis of a frequency modulated square wave. So square wave is where, so instead of the sort of gradual up and down motion of a sinusoidal wave, it just alternates between two values. a higher value and a lower value. That's a square wave. And then the frequency modulation means that instead of it being exactly equally spaced, the transitions between the two, they're getting gradually shorter and longer, and shorter and longer. And so what we see in this time frequency analysis, the lowest frequency component, that represents the actual frequency modulation of the square wave, but then you have these other components at higher frequencies. These are the harmonics that are sort of being detected in this time localized analysis that tells you that in sort of locally around each moment in time, the signal is not sinusoidal but something else, and in fact it's very non-sinusoidal, which is why we have so many of these harmonics. Again, these are at integer multiples of the fundamental frequency. And a key point that one needs to be aware of in time frequency analysis is the Heisenberg-Gabor uncertainty principle. So one often hears about the Heisenberg uncertainty principle in quantum mechanics, but it's really a mathematical principle. It's not specific to quantum mechanics, and so it's very important as well in time frequency analysis. And in terms of its time frequency analysis application, it can be described heuristically as follows: that in time frequency analysis there's always a trade-off between time localization and frequency resolution. Namely, to have a sufficiently sharp or non-blurry description of the frequencies present in the signal around any given moment in time, you need to take account of how the signal behaves in a sufficiently wide time interval around that moment in time. But doing so means that your temporal changes in the frequency content are shown as more blurred in time, because you've had to use a wider time window to get the sense of the oscillations in the time window. Roughly speaking, mathematically, there is a kind of universal lower bound on the product of the blurriness of representation in frequency and the blurriness of representation in time that time frequency analysis will give you. So let me now show you. Here is a time frequency analysis of a signal. It's a numerically generated signal, but I'm going to show you another time frequency analysis of the same signal, and I'm going to show you yet another one. And so what you see, so if I go from the first to the second to the third, the vertical amount of blurring is decreasing. In other words, the frequency resolution is increasing. But if you look, say, at the middle oscillation, so I'm now on the second of the three time frequency analyses that I showed you. As I go from the second to the third, if you look at that middle of the three oscillations, you see now it's become slightly more horizontally blurred. So as I increased the vertical resolution, which is the frequency resolution, the horizontal resolution, that's the time localization, has decreased as the time window has widened. And so for every time frequency analysis implemented in Moda, one of the parameters that the user controls is a frequency resolution parameter that controls the trade-off between the frequency resolution and the time localization. So in the first of these that I showed you, the frequency resolution parameter was set to 1, in the second it's 2, and in the third it's 4. There are two types of time frequency analysis in Moda. One is called the windowed Fourier transform, and the other is called the wavelet transform. And the latter treats frequencies in a kind of logarithmic manner, and that is useful because it enables one to resolve the time-evolving characteristics of oscillations occurring across a broad range of timescales simultaneously. Whereas with the windowed Fourier transform, if you've got frequency, or you've got oscillatory components at a wide range of frequencies, then you would really need to sort of look specifically in different frequency ranges and reapply the windowed Fourier transform in each of these different frequency ranges, because it doesn't have this logarithmic frequency treatment that's able to simultaneously span a multiplicatively broad range of frequencies. And so this is the essence of the M in Moda, for multi-scale, because the wavelet transform has this sort of multi-scale resolution capacity. So then let me briefly mention the other methodologies in Moda that all build on time frequency analysis. So one is wavelet phase coherence, which investigates common oscillatory influences between two simultaneous signals X and Y. And then next is ridge extraction, which can extract and reconstruct individual oscillatory components from a signal. Then we have wavelet bispectral analysis, which investigates the presence of interactions among oscillatory components of different frequencies. Dynamical Bayesian inference, which seeks to infer a time-evolving dynamical system that describes how two oscillatory processes influence each other's rate of progression through their respective cycles. These three methods come with the facility for doing hypothesis tests for testing the significance of the results using numerically generated surrogate data. Okay, that's all. Thank you very much.
Thank you for that fascinating and engaging talk, Julian. Hope you guys enjoyed that. If you would like to download Moda for your own usage, you can do so for free. Just follow the link in the description below to the GitHub page, and you'll currently need MATLAB to run that. Now, we've got one more exciting nugget for you today before we leave you, and that is that Julian is starting his own YouTube channel at present. Now, it's currently in a relatively nascent, unformed state, but if you follow the link in the description below to the channel and subscribe, you will get all sorts of mathematical goodies pouring into your YouTube feed in the near future. So go and do that, and thanks for watching, and we will see you next time.
This video is brought to you by EasySkips.online, the quickest, easiest way to order a skip.
What can we do with this skip, Eve?
Camp. Balance. Science.
So we're now generating 115 Hertz from the speaker, and we're measuring the amplitude using this app at this side of the skip. So I'm going to change the frequency, and we're going to see what happens to the amplitude. But I'm going to have to shut up while I do it, because otherwise this is just detecting my voice. Whatever you do with your skip, make sure you get it from Easy Skips.
The clue's in the name.